Hello everyone, I am V. Sarumati, Assistant Professor in the Department of ECE from SRM Madurai College for Engineering and Technology. In this video, we are going to see about the review of number systems, which is the first topic in Unit 4 Digital Electronics in BE 3251 Basic Electrical and Electronics Engineering. Now let's see what is number system. Number systems are fundamental in digital electronics. They provide a way to represent the data and process the data using binary logic. The most commonly used number systems are decimal number system, binary number system, octal number system, hexadecimal number system. Now let's see the number systems one by one. At first, we will see the decimal number system. Decimal number system has 10 digits from 0 to 9. Since it has 10 digits, so its base is 10. Next, coming to the place value, each digit's value depends on its position and it is a power of 10. Let's consider this example 345 to the base 10. This is a decimal number. Now considering this, each digit's value, here the digit 5, its digit's value depends on its position, where it is placed. 5 is placed at the ones position and it should be a power of 10. So, we should represent the ones position as 10 to the power 0. So, it is 10 to the power 0 is 1. So, it is in ones position. Next, consider this digit 4. Since it is in the tens position, so we can write this at the power of 10 as 4 into 10 to the power 1. Next, 3. The digit 3 is in hundreds position. So we can write this hundreds position in terms of powers of 10 as 10 to the power 2. So this is how we are representing the place value. Next, as we have seen earlier, 345. 3 into 10 to the power of 2 plus 4 into 10 to the power of 1 plus 5 into 10 to the power of 0. Here the powers of 10 is considered as weight. The weight is the position of each digit in a decimal number. It is the position of each digit. Here for the digit 3, its position is 10 to the power 2. That indicates the magnitude of the quantity and can be assigned it as weight. So weight is the power of 10 here in the decimal number system. For the whole numbers, weight are the positive powers of 10 increasing from right to left. So right to left, it is the increasing powers of 10. For the fractional numbers, it is a negative powers of 10 that is decreasing from left to right. The fractional number that is after the decimal point, it is the powers of 10 that is negative powers that is in the decreasing. 10 to the power minus 1, minus 2 and minus 3. It is decreasing from left to right. Next we will see about the binary number system. Binary number system has two digits 0 and 1. These digits are also called as bits. Since it has two digits, so its base is 2. Binary numbers are used in digital circuits. Here the on state is considered as 1 and off state is considered as 0. Let's see an example. Like that in the decimal number system, each digit is represented by its position, that is in terms of powers of 10 in decimal number. But in case of binary system, here the base is 2. So we have to replace the 10 by 2. Since it has a base of 2. So we can multiply each digit with its corresponding position, that is corresponding power of 2. So here 1, it is in ones place, so we are multiplying 1 with 2 power 0. 2 power 0 is 1. Okay. Then the next bit is 1 into 2 power 1. It is in tens place. So we can write it as 2 power 1. So 1 into 2. Next bit is 0. 0 into 2 power 2 is 0. And the last bit is 1 into 2 power 3. It is more significant bit is 1 into 2 power 3, which is 1 into 8. So by summing all these things, we will get 11, which is a decimal number. This is how we are converting binary to decimal number. This is an example for. Now let's see an example to convert binary number to decimal. Here binary number is represented by ones and zeros. So this binary number 110101. First we have to write the binary number, and now we have to write its weight. That is, for each digit we have to write its weight. Here weight in the sense, in terms of powers of 2, we have to write its positional value. So starting from the least significant bit, that is from right to right. Here for the position, this for the digit 1, we have to represent its weight as 2 power 0. That is an increasing order of increasing powers of 2. We have to mention it. These are all we have discussed in the previous slides. In place of for the digit 0, it is 2 power 1, and this for this 1, it is 2 power 2. Like that it goes on. The next we have to multiply each digit with its weight. So 1 into 2 power 0 is 2 power 0, plus 0 into 2 power 1 is 0. So we didn't, 0 into 2 power 1 is 0. So we didn't write here the 0. Then 1 into 2 power 2 is 2 power 2, plus 1 into 2 power 3 is 2 power 3, plus 0 into 2 power 4 is 0. So we didn't write here. And 1 into 2 power 5 is 2 power 5, plus 1 into 2 power 6. And 2 power 6 value is 64, 2 power 5 is 32, and 2 power 3 is 8, and 2 power 2 is 4, plus 2 power 0 is 1. Summing all these, we will get the value of 109, which is the decimal number. This is how we are converting binary number to decimal number. Here we are converting fractional number, binary number to decimal. Here this is also same like that of the previous one. Here also we are writing the binary number 0.1011. Here too we are writing the weights for this fractional number. Here in after the decimal point, since it is a fractional number, so after the decimal point we have to represent the position of the bit in terms of negative powers of 2. So since it is a fraction, after the decimal point we have to represent it here as a negative power, that is in the decreasing order from left to right. So here for the digit 1 it is 2 power minus 1, and 0 2 power minus 2, and 1 2 power minus 3, and here for the last bit 2 power minus 4. So 1 into 2 power minus 1 is 2 power minus 1. Then 0 into 2 power minus 2 is 0. That's why it is not mentioned here. And 1 into 2 power minus 3 is 2 power minus 3, plus 1 into 2 power minus 4 is 2 power minus 4. And 2 power minus 1 is nothing but 1 by 2. 1 by 2 value is 0.5. Similarly, 2 power minus 3 is 1 by 2 power 3, which is 0.125. And similarly, 2 power minus 4 is 0.60625. By summing all these things, we will get 0.6875, which is a decimal equivalent of this fraction binary number. Here is a conversion of decimal to binary. There are two methods to convert decimal number to binary system. One is sum of weights method and repeated division method. Now first let's see sum of weights method. Here in the name itself, we are summing the weights. Let us consider 9, this number, decimal number. First, we have to represent this 9 in terms of powers of 2. So, we can write 9 in terms of powers of 2 as 8 plus 1. 8 is 2 power 3 and 1 is 2 power 0. Okay. Next. Now in the next step, we have to write the two powers in increasing order from right to left. 2 power 0, 2 power 1, 2 power 2 and 2 power 3. Now we have to place, if this two powers is present in this representation of decimal number, we can place ones in that appropriate weight position. So here in this 9 representation, 2 power 3 is present. 2 power 3 and 2 power 0 are present. So we can place 1 in this appropriate position of 2 power 3 and 2 power 0. For the remaining positions 2 power 2 and 2 power 1, we have to place it as 0. So placing ones in the appropriate bit positions, here 2 power 3 and 2 power 0 as position, we have to place 1. And for the remaining 2 power 2 and 2 power 1's position, we have to place 0. And this is the binary equivalent of 1001 is the binary equivalent of the decimal number 9. Similarly, we have some other examples, equivalents of these decimal numbers, all these decimal numbers. Next is the repeated division by 2 method. Here in this method, here also from the name itself, we have to repeatedly divide the number by 2. Divide the decimal number by 2 until the quotient is 0. Quotient becomes 0, we have to divide it repeatedly. The remainders form the binary number. Now let's consider the number 12. We have to divide the number 12 by 2. The quotient here is 12 by 2 is 6. The remainder for this division is 0. Next the quotient again is 6. 6 by 2 is 3. The remainder is 0. Next the quotient is 3. 3 by 2, the quotient is 1. Remainder is 1. Next, 1 divided by 2 is 0 point something. So the quotient becomes 0. So we have to stop till this. And here the remainder is, this 1 itself is a remainder. So we have to mention from left to top in terms of representing the binary equivalent. So we have to mention it as first the down remainder. 1, then 1, then 0, then 0. This is bottom to top approach. So here the MSB is the last one and LSB is the first one. So this is the 1100 is the binary equivalent of the decimal number 12. Here are the examples for decimal fractions to binary conversion. Here also the sum of weights method contains the same procedure as that of the whole numbers, but after the decimal point, we have to mention it as the negative powers of, we have to represent in terms of negative powers of 2. So first 0.625 can be represented in terms of powers of negative powers of 2 as 0.5 plus 0.125 and 0.5 as 2 power minus 1 and 0.125 is nothing but 2 power minus 3. And for the representation after the decimal point, we have to mention this. If 2 power minus 1 is present, so we have to place 1 in the position of 2 power minus 1. And here 2 power minus 2 is missing, so 0 for in the position of 2 power minus 2. And 2 power minus 3's position, we have to place 1. So the binary equivalent for 0.625 is 0.101 in sum of weights method. So next one is repeated division by 2 method. Here instead of division, since it contains a fractional part, so instead of division we have to multiply it by 2. So 0.3125 is multiplied by 2, which gives 0.625. This carry has to place here. Next 0.625, again repeatedly we have to multiply it by 2. Till the fractional part becomes 0, we have to multiply. So 0.625 into 2 is 1.25. So the carry here is 1. For the next step, we have to omit the carry and we have to bring that fractional part alone. So 0.25 into 2 is 0.50. Here the carry is 0. Next 0.50 into 2 is 1.00. Here the fractional part after the decimal point, the fractional point is 0. So we have to stop till this. And now the carry is 1. So here it is top down approach. So we can write from this first carry. Point after the decimal point, 0, then 1, 0 and 1. And this is the a binary equivalent for the decimal fraction.